When I think of Philips, two words come to mind: presence and innovation. I think of presence because Philips is everywhere. Philips is one of the largest companies in the world. I think of innovation because Philips is a technology innovator and we're a market leader in electronics. We've invented products that most people take for granted, like the cassette tape player and compact disc. Philips is the ADC51 market leader with the largest sales and the most derivative products. We've brought many innovative ADC51 products to market, and Philips is continuing to lead the innovation in that market. For this reason, we've been listening to our customers, and they've been asking us for microcontrollers that have much higher performance, greater memory addressing range, and better support for high-level languages. So we developed the XA architecture based on this input, an architecture that's compatible with the ADC51 and yet has very high 16-bit performance. The XA was designed to work efficiently with code that's written in a high-level language like C. We also added a number of instructions and architectural features to support the execution of high-level code. The XA offers Philips customers the best value of any 16-bit microcontroller available. The XA has a 16-bit static CPU core and 16 megabyte addressing range. This offers plenty of power today and plenty of room to grow. One of the things we focused on was processing times. A 16 by 16 multiply takes just 480 nanoseconds to execute with a 25 megahertz clock. This is fast. The core of the XA has a register file that eliminates the accumulator bottleneck that exists with older architectures. There's up to 32 vectored interrupts and up to 16 hardware exceptions and 16 traps available to the user. From the XA architecture, we're going to develop a derivative family just like we have with the ADC51. The Philips ADC51 family is the largest in the market today. We'll do the same thing with the XA by adding various sizes of memory, I/O ports, serial interfaces, timers, math blocks, and a wide variety of other features like A to D and PWM that will complement the core. One of the things that we have strived for with the XA is to make it easy to understand and use. The XA has the same basic core structure as the ADC51. There is the data address control bus that is separate from the SFR bus. There are the separate data memory and program memory spaces and buses. This compatibility with the ADC51 has in no way limited the performance of the XA. You can see the XA has a 16-bit ALU and 16-bit data paths. This is a true 16-bit microcontroller. Performance is 2 to 4 times better than today's best-selling 16-bit microcontrollers. Now let's look into the core and see the advanced features of the XA. We increased the program memory space to 16 megabytes. It's a linear space. The XA executes from on-chip memory unless either the EA pin is grounded or a fetch is attempted from an address that is higher than on-chip memory. In this case, the XA will execute from external memory. This is identical to the operation of the ADC51. The XA instruction set has been upgraded to allow jumps, calls, and branches across the whole 16 megabyte space. Page Zero mode is a capability we've added to the XA for applications that require less than 64K of memory. In Page Zero mode, the XA will make 16-bit fetches from the memory for all address-related instructions. This saves memory space and execution time. Page Zero mode is entered by setting the PZ bit that's located in the system configuration register. The interrupt vector table is located at the bottom of the program memory space, just like it is in the ADC51. In fact, it can't be emphasized enough that the structure of the program memory, data memory, and the programmer's model of the XA is identical to that of the ADC51. The data memory is also a 16 megabyte space, and the memory is broken up into 256 pages, each 64K in length. Each of the pages have the same characteristics in terms of bit addressable and direct and indirect addressable spaces. Each page is directly addressable for the first 1K bytes. After that, it is indirectly addressable. The bit addressable space between 20 and 3F hex is duplicated in each page. Addressing data memory is easy because there are two registers, the DS and ES. When they're appended to a register file register, you get a 24-bit address that can access the full 16 megabytes of data memory. There are 8 word registers in the register file, and any of these can be used as data pointers to the data memory. By switching between the two segment registers, DS and ES, it's easy to pick up data and move it in memory. The register file is a very powerful feature that eliminates the accumulator bottleneck that exists in most older architectures. To be compatible, we've mapped the ADC51 accumulator, extension, and data pointer to specific registers in the XA register file. For example, a translated ADC51 code that calls out the accumulator will use register R4L. And the nice thing about the XA is that once the code's translated, you can change the register designator if you wish. The least significant 4 words in the register file are banked and across 4 banks that total 16 words. In the ADC51, there are 4 banks of 8 registers at the bottom of the data memory space. This structure was maintained in the XA to stay compatible. Instead of implementing it in the data memory space, though, we put it in the register file. For compatibility, the least significant 4 words of the register file can be mapped into the least significant 32 bytes of data memory. Even though they're mapped into data memory, they still have all the functionality of a register file register. In total, you have 21 word registers in the register file, and they are all bit addressable. It's very powerful. The special function registers are the registers through which the XA peripheral features such as timers, ports, serial interfaces, or A to Ds communicate with the core. The SFRs are all directly addressable as in the ADC51. There is 1K bytes of SFR space, 512 bytes on chip, and 512 bytes mapped into the external memory space. The stack on the XA is different than that on the ADC51. The ADC51 stack grows up and is limited to the 256 bytes of on-chip data memory space. The XA stack on reset resides at the highest location within the internal data memory and grows down. The stack can reside on-chip or off-chip anywhere in a 64K page. And the XA stack is word-oriented, which means it always pushes or pops 2 bytes. For addressing information in memory, the XA includes a number of enhancements, specifically more powerful data type handling and more flexible addressing modes. While the ADC51 dealt with a few 4-bit and mostly 8-bit numbers, all unsigned, the XA can handle all of these, as well as 8-bit signed and 16-bit signed and unsigned numbers. The XA supports all of the ADC51 addressing modes, including direct, indirect, immediate, bit, and SFR addressing. In addition to these, the XA has 2 powerful new modes of addressing, indirect with auto-increment and indirect with offset. In the auto-increment mode, the register file register R4 is appended to either the DS or ES register to indirectly address memory. Then the immediate value is subtracted in the ALU from the value in that memory location. This result is placed back in memory, and R4 is incremented to point to the next memory location. In this example of the indirect with offset addressing mode, a value is being added to the R6 register of the register file. At the start of the operation, a signed offset value is added to the R4 register. The resulting value in R4 is used to indirectly address data memory. Then the value in the address memory location is added to the value in R6, and the result stored back in R6. The processor status word, or PSW, is the heart of the CPU itself. In the XA, it has greater functionality than existed in the ADC51. To be compatible with the ADC51, we duplicated the PSW of the ADC51, but we also wanted to add power to the XA, so there are actually 2 PSWs in the XA. If you're in ADC51 compatible mode, the XA uses the ADC51 PSW. All of the rest of the time, the more powerful XA PSW is used. The low byte of the XA-PSW is similar to that of the ADC51. There is the carry flag, the auxiliary carry flag, and the V overflow flag, just like the ADC51 PSW. These have the same function as in the ADC51, except that the carry flag, auxiliary carry, and the overflow flags will reflect the status of the last register that's been operated on in the register file. The new flags that are added in the low byte are the N-negative flag and the Z0 flag. The negative flag shows the sign of the 2's complement result of an arithmetic operation. The 0 flag is set if the result or value in the register is 0, otherwise it's cleared. These flags also reflect the status of the last register that's been operated on in the register file. With these flags, you can get more information on the result of the last operation than you can with the ADC51P parity flag. The high byte of the XA-PSW has a number of new bits. The SM or System Mode bit is used in multitasking applications. When set to 1, the XA will operate in System Mode, and when cleared, it will operate in User Mode. The TM or Trace Mode bit is primarily used in development tools. When set, it enables the built-in debugging facilities of the XA. Bits RS0 and RS1 select which register blank to use. The last 4 bits in the high byte of the PSW allow you to set an interrupt mask level for the code that's executing. This is a very powerful feature that allows you to more closely control the execution of code within the XA. Another core register is the System Configuration Register, or SCR. This register contains the page 0 and compatibility mode bits. The PT1 and PT0 bits allow you to adjust the speed at which the peripheral functions on an XA derivative are clocked. We added this feature to give you more control over the interface of the on-chip peripherals to the rest of your design. The reset on the XA is active low to simplify your system design. On reset, the XA begins execution at location 0 in the program memory, just like the ADC51. There are 4 bytes of code here that make up the reset vector. The first 2 bytes are loaded into the PSW register. This allows you to set the interrupt mask and put the part in system mode. The next 2 bytes are loaded into the program counter and are the address where you've located the reset interrupt routine. Once you've reset the XA, you're ready to run some code. The XA instruction set is compatible with the ADC51 instruction set and also has a large number of new, more powerful instructions. The XA instructions have a 1-to-1 correspondence to ADC51 instructions. This means that for each ADC51 instruction, there is a corresponding XA instruction. Some of the instructions have been enhanced to give you more capability than exists on the ADC51. For instance, we've included a short add instruction in the XA. This is used in place of the increment instruction that existed on the ADC51. With the short add, you can add any integer value between -8 and +7 to a register. There are also all of the ADC51 jump, call, and return instructions, as well as several new ones that allow you to access the whole 24-bit address range of the XA. The branch instructions have been beefed up significantly to allow you to do with one instruction in the XA what would take many instructions in other architectures. All of the math operations can be performed in the XA with signed or unsigned variables. The multiply, divide, and shift instructions have been enhanced to take advantage of the XA's 16-bit ALU. Notice that there is a 32 by 16-bit divide instruction, and that shifts up to 31 bits can be performed with one instruction. While adding power to the XA, we didn't lose sight of your need for the smaller but still very important instructions. All of the bit manipulation instructions from the ADC51, which are so important in many embedded applications, have been included in the XA. To make your programming efforts easier, we've added a number of other instructions like the sign, extend, and normalize instructions that make it easier to implement floating point operations. The XA also has a software breakpoint instruction and a software reset instruction that resets the XA just like the hardware reset. While we've given the XA a powerful instruction set, that's not all we've done. Interrupt and exception handling have been substantially improved within the XA over the ADC51, not only because of the addition of exception handling, but also the restructuring of the interrupts to make them much more powerful. The interrupt vector itself consists of two words, the first being the processor status word, PSW, which allows you to change the priority level of the interrupt service routine from the priority of the interrupt itself. The second word is the address of the service routine. The XA supports 32 interrupts with 16 priority levels. The interrupt priority level of each interrupt can be set in its interrupt priority register. This gives you more control over what can interrupt the executing code than with the ADC51, where there are only 2 priority levels. Of course, the interrupts can be enabled or disabled. The XA also has software interrupts, which allow you to change the interrupt priority of an executing interrupt. This table shows the various software interrupts. The XA supports 16 exceptions and 16 traps. The trap instructions are under the user's control and can be placed anywhere in the program code. Exceptions are fixed and allow the user to deal with things like breakpoint, trace, stack overflow, divide by zero, or executing an RETI in user mode. The exceptions and traps are serviced just like an interrupt, with the vector table located at the bottom of page 0. From the table, a PSW value and address for the service routine are loaded. Except for reset, the current program counter and PSW are pushed onto the stack whenever an exception or a trap are executed. This makes it possible to return to the conditions you had before the exception or trap occurred. The XA has built-in capabilities for the support of multitasking. This support is easy to use and yet powerful enough to offer a real framework for implementation of real-time systems. There are 2 privilege levels, System and User, that determine how much access a given task has to registers within the XA. The System level has full access, while the User level has limited access. For further protection, there are 2 stacks, the System stack and the User stack. The System stack resides in page 0 of the data memory, while the User stack resides in the page of data memory that the user has assigned to the task. Within this structure, a complete multitask application can be easily implemented. On the XA, we've created a very flexible external interface that allows users to connect to a wide range of memories and peripheral chips. The XA supports both an 8-bit and 16-bit external interfaces. This is a diagram of an 8-bit external interface for the XA, which is very similar to that for the ADC51. An exception is this derivative of the XA can address 1 megabyte of memory, so it has 20 address lines. It also differs in that the least significant 4 bits of the address are not multiplexed with the data lines. This allows you to do burst transfers of up to 16 bytes from external memory with 1 ALE. Not having to switch ALE means that the data can be transferred in 2 clocks instead of 3, so you can keep the program queue full and execute instructions without stalling the CPU. This is an example of the 16-bit external interface connection. Notice that it's similar to that of the previous diagram, but has a 16-bit wide data bus. With the XA, one of the design goals was to give you as much flexibility as possible when using the part. Let's look at the registers in the XA that control its external interface. In the bus configuration register, BCR, are the bits to disable the external interface and the wait states. Setting the bus D bit to 1 will prevent the external interface from trying to make any off-chip memory fetches. The wait D bit disables the wait states so that they will not affect the exchange of information with external memory or components. The number of bits in the external interface and the number of address lines are determined by the BC2, BC1, and BC0 bits in the bus configuration register. By setting these bits, you can choose between combinations of 8-bit or 16-bit external interfaces and 12, 16, 20, or 24-bit address lines. Reducing the number of address lines allows you to use the extra pins as I/O. The bus timing is controlled in the bus timing register, BTR. By changing the value of the high byte of this register, you can control the width of the data write and data read signals. DW and DR control the width in burst mode, without ALE, while DWA and DRA are used with ALE. The data write and data read signals can be extended by 1, 2, or 3 clocks. From the low byte of this register, you can control the width and data hold time when in write mode, the width of the ALE, and the width of the program memory read cycle with or without ALE. The XA also has an external wait pin. If you cannot get enough delay from the programmable wait states, you can use the wait pin to delay the XA for as long as necessary. Each of the I/O pins on the XA have a programmable output structure. This means you can determine the output structure for each pin: open drain, ADC51 quasi-bidirectional, high impedance, or push-pull. On reset, all of the outputs come up in a predefined state that depends on the XA derivative. The technical features of the XA make it a high-performance 16-bit microcontroller that's also compatible with the ADC51. XA source code is compatible with the ADC51, meaning there's a one-to-one relationship between each ADC51 instruction and a corresponding XA instruction. The XA memory map is a superset of the ADC51 memory map. It has the same programmer's model and the specific ADC51 registers, like the accumulator, the extension register, the data pointer, the stack pointer, and PSW, have all been preserved within the XA. While compatible, there are some things to consider if you're thinking about migrating your design from the ADC51 to the XA. If you have ADC51 code that depends on the timing of the instruction sequence, you'll have to adjust the code for the XA, which runs at a much higher internal speed and has a different timing relationship to the code. If you have ADC51 code that depends on the precise stack location, you'll need to adjust the code. The stack in the XA has been relocated and grows down rather than up, as in the ADC51. So there will be differences in placement in the data memory. Any direct reference to the stack pointer, since the stack pointer is now 16 bits rather than 8, should also be looked at. Any tables that rely on instruction length to calculate an index value will have to be adjusted because an XA instruction may have a different length than the corresponding ADC51 instruction. There are over 24 third-party vendors now supplying tools for the XA. Among those tools are C compilers, emulators, programmers, development boards, target boards, assemblers, simulators, translators, linkers, and real-time operating systems. The right tool is available for the XA to meet the demands of your application as well as the demands of your pocketbook. In many of these tools, the software interface on the PC is the same as for the ADC51. You won't need to learn to use the software interface because they're from the same companies with which you're already familiar. There are also data books, application notes, and user guides available for the XA. Philips also has an internet site with a lot of software you can freely access, including some basic software development tools. Philips is developing a range of derivatives based on the XA, just as we've done for the ADC51. The first derivative, the XA-G3, is available now. We will continue to develop the XA core, as well as adding more powerful features and enhancing the performance. While the core is operating at 25 MHz today, we intend to push that performance up over 100 MHz. The XA is a 16-bit architecture that's compatible with the ADC51, yet that doesn't hinder its performance as a 16-bit microcontroller in any way. The XA has enough performance to meet your 16-bit needs today and well into the future. With the XA, Philips is extending the power of the ADC51 and has given you an easy migration path to high-performance 16-bit embedded control.